Good morning, students. In the previous session, we have seen Nernst equation, that is the derivation of Nernst equation and applications of Nernst equation and Nernst equation at room temperature. But before that, just let us recall the Nernst equation, only the Nernst equation. The Nernst equation is the relationship between electrode potential and the standard electrode potential, temperature, and reaction quotient. So E is equals to E naught minus 2.303 RT by NF log Q or K. That is the Nernst equation, general Nernst equation. Nernst equation at room temperature is E is equals to E naught minus 0.059 by N log Q or K. By substituting T value, F value, R value, we can get the Nernst equation at room temperature. Yes. So that was the previous class. So now in this session, I'm going to explain you numericals on Nernst equation, reference electrodes. In reference electrode, totally we are having 3 electrodes. But today I'm going to explain the 2 electrodes. One is saturated calomel electrode and the quin hydrone electrode. And one more electrode is there, that is ion selective electrode, that is the glass electrode, that I will explain in the next class. And the applications of saturated calomel electrode and the quin hydrone electrode. So first let us see the numericals on Nernst equation. But before that, what is the Nernst equation? E is equals to E naught minus 0.059 by N log K or 2.303 RT by NF log K or Q. So let us see the first numerical. The standard electrode potential of zinc ions is 0.76 volts. So you know what is standard electrode potential? E naught. E naught is standard electrode potential of zinc is 0.76 volts. And what will be the potential of the 2 molar solution at 300 K? So what they have given? They have given E naught value and the concentration value and also the temperature. They have given absolute temperature in Kelvin. So we no need to convert the centigrade into Kelvin because already temperature in the Kelvin. So solution, the Nernst equation for the given conditions can be written as E is equals to E naught minus 2.303 RT by NF log 1 by Mn plus. So we know how to write the reaction. Zinc is giving rise to Zn plus 2 plus 2 electrons. So that is the reaction for zinc. Yes. So what is the reaction for zinc? Zn giving rise to Zn plus 2 plus 2 electrons. Yes. So this is the reaction. But what is the Nernst equation? E is equals to E naught minus 2.303 RT by NF log K or Q. So what is K here? Products concentration divided by reactants concentration. But here we have seen the reverse reaction, that is Mn plus giving rise to M. Mn plus giving rise to M is nothing but the products are reactants are Zn plus 2 electrons and the product is Zn. So we need to write like this because they asked for the oxidation reaction. Yes, so this is the reaction. So see, E Zn plus 2 by Zn is equals to E naught minus 2.303 RT by NF log product is Zn. So Zn concentration divided by Mn plus concentration. What is Mn plus here? Zn plus 2 is Mn plus. So but why Zn concentration is 1? Because zinc is a solid. Solid concentration always equals to 1. Yes. So 1 divided by Zn plus 2. So now let us see In the numerical, they have given E naught value, temperature value, and also the concentration of the given solution. So we know the F value, that is the Faraday constant value. And what is N? N is the number of electrons. But how many electrons are there in the numerical? 2 electrons. So N value is 2. Faraday constant is approximately 96,500 coulombs per mole. R is 8.314 joules per Kelvin per mole. So let us substitute E naught 0.76, N number of electrons 2, Faraday constant 96,500 coulombs, and Mn plus 2 because they have given the concentration. Mn plus 2 concentration is 2 molar. R is 8.314 joules per Kelvin per mole, and they have given the absolute temperature, that is 300 K. So let us substitute all the values in the formula. E is equals to E naught. What is E naught? 0.76 minus 2.303. R is 8.314 into, what is T here? T is the 300 Kelvin divided by N is 2, F is 96,500 into log 1 by 2. Yes. So let us simplify this. 0.76 minus after multiplication and the division, we got this. And finally 0.76 plus, by doing simplification, we will get 0.009. So finally we got 0.769 volts. This is the electrode potential of the zinc in a reduction reaction. Yes. So this is the first numerical. So simply you have to write the reaction part first. After writing the reaction part, just apply the Nernst equation. Apply the Nernst equation. So whatever the values they have given in the numerical, substitute those values. And R value is a known value, F value is a known value. But you have to remember those values. Yes, by substituting all the values in the formula, we will get electrode potential. Now the next one, what is the cell potential of the electrochemical cell? So in this numerical, they are cell potential. So what is cell potential? E cell is the cell potential. Yes. So previously we applied only for one electrode. Yes. We have applied only for the reduction. But here they have asked for the complete reaction, that is E cell. What is the cell potential of the electrochemical cell in which the cell reaction is? See, they have given the complete cell reaction. You know how to write the complete cell reaction by adding anodic reaction and cathodic reaction. We will get like this. Pb plus 2 plus Cd giving rise to Pb plus Cd plus 2. Given that E naught cell is equals to 0.277 volts, temperature is 25 degrees centigrade, Cd plus 2 concentration 0.02 m, and Pb plus 2 concentration is 0.2 m. Yes. So now what is the Nernst equation for E cell? E cell is equals to same formula. E cell is equals to E naught cell minus 0.09 by N log Q. Previously, we have written 2.303 RT by NF into log K. But here, we have written 0.059 by N log Q. Why? Because they have given the temperature as room temperature. But we know what is the Nernst equation at room temperature. At Nernst equation, at room temperature, Nernst equation is E cell is equals to E naught cell minus 0.059 by N log Q. Yes. So now let's see what is N, what is Q. Q is the reaction quotient. Reaction quotient is nothing but products concentration divided by reactants concentration. In the previous class, I explained you how to write the reaction quotient for the given reaction. Yes. So for one reactant, how to write the reaction quotient. For the two reactants, how to write the reaction quotient. Yes. But what is reaction quotient here? Products concentration divided by reactants concentration. So see here, Q is products concentration divided by reactants concentration. But what is the reaction here? This is the reaction. What are the products here? PV and CD plus 2 are the products. PV plus 2 and CD are the reactants. So let us write the Q value here. So let us write Q here. What is product here? PV is the product. PV is the product. And what is another product here? What is another product here? Another product is CD plus 2. So we need to write plus 2 only here, divided by reactants concentration. What is reactant here? PV plus 2 and CD. PV plus 2 and C. So now see here, Q is equals to product concentration divided by reactants concentration. But here we know PV is a solid, lead is a solid, and cadmium, that is also solid. I explained you in the previous class that it's a metal without charge, that is solid, that is the metal. If metal with charge, that means if the metal is the ion, that is electrolyte. See here, PB and CD are without charge. So these are solids, that is the metal. So PB and CD concentrations are equals to 1. And here CD plus 2 and PB plus 2 are having charges. So that is electrolyte. So electrolyte concentration given in the numerical. So see here, PB concentration, CD concentration is equals to 1. And what is CD plus 2 concentration given in the numerical? That is 0.02 m. And given PB plus 2 concentration also in the numerical, that is 0.2 m. So by substituting these two values, we will get Q is equals to 0.02 divided by 0.2 m. So see here, 2 moles of electrons are transferred in the reaction. So because of that reason only, we got 2. CD is losing 2 electrons to produce CD plus 2. PB is losing 2 electrons to produce PB plus 2. Yes. So here the number of electrons are 2. If you don't remember the number of electrons, if you can't write the number of electrons, at least look at the charge. See here, what is the charge? 2 is the charge. Yes. So if we have PB plus 3, PB is losing 3 electrons. That's the reason we got PB plus 3. If we have PB plus 4, PB is losing 4 electrons. That's the reason we got PB plus 4. Yes. So look at the charge. You can identify the number of electrons here. So here 2 is the number of electrons. So here 2 moles of electrons are transferred in the reaction. Therefore, N is equals to 2. Now the reaction quotient is given by CD plus 2 divided by PB plus 2. Because CD and PB concentrations are equals to 1 is equals to 0.02 by M divided by 0.2. So we will get 0.1. So now we got Q value as 1. Q is 1 and N is 2. And E naught cell value given in the numerical, that is 0.277. So we can find E cell. So E cell is equals to E naught cell 0.277 minus 0.059 by number of electrons 2 into log Q is 0.1. So by substituting all the values and after simplifying, we will get 0.277 minus 0.0296 into minus 1, that is equals to 0.3066 volts. Yes. So this is the cell potential value by applying the Nernst equation. Yes. So now let us see the last numerical on Nernst equation. The Cu plus 2 ion concentration in a copper-silver electrochemical cell is 0.1 m. Here also they have given the cell. If E naught of Ag plus by Ag is equals to 0.8 V and E naught of Cu plus 2 by Cu is equals to 0.34 volts and cell potential at 25 degrees centigrade. Here also they have given a 25 degree centigrade. So we need to use the same formula, that is 0.059 by n is equals to 0.422. Then find the silver ion concentration. So what they are asking? They are asking the concentration of silver ion. Yes. So they have given the E naught values of the single electrodes. But what we need to find here? We need to find the silver ion concentration. Yes. So here the silver electrode acts as the cathode. So we are having the two electrodes. But here silver electrode is acting as a cathode, and where the copper electrode serves as the anode. This is because the standard electrode potential of the silver electrode is greater than the copper electrode. So how do you know that this electrode potential is high, this electrode potential is less? Based on the electrochemical series. Yes. So that we have seen in the previous class. In electrochemical series, the top metal is always acting as the anode, bottom metal is always acting as the cathode. So here silver electrode is at the bottom position and copper electrode is at the bottom position, so top position. So copper is acting as the anode and silver is acting as the cathode. So if copper is acting as the anode, it should undergo oxidation. Here silver is acting as a cathode, so it is undergo reduction. Yes. So you know what is oxidation? That is loss of electrons. Reduction means gaining of electrons. That means silver is gaining the electrons, copper is losing the electrons. So let us write the Nernst equation. E naught cell is equals to, but first let us calculate the E naught cell value. But you know the EMF. Yes. So EMF of the cell or EMF of the standard cell. So what is EMF? E cathode minus E anode. So numericals of EMF also we'll do in the next class. Already we have done the numerical. So EMF is equals to EMF of standard cell is equals to E naught cathode minus E naught anode. But they have given E naught values of 2. But now we know which is cathode, which is anode. E naught of silver is cathode, copper is anode. So cathode value is 0.8 minus anode value 0.34. After subtracting, we will get 0.46 volts. So what is this? This is E naught cell. But we know the E cell formula from Nernst equation. E cell is equals to E naught cell minus 0.059 by N into log Q. So now we know what is E naught cell from here. E naught cell is 0.46 minus 0.059 by 2 because number of electrons are 2. Because you can see the maximum charge here, the maximum charge is 2 into log Q. So Q is nothing but product's concentration divided by reactant's concentration. So what is product here? Cu plus 2 is product and Ag plus is reactant. But they have given the concentration of Cu plus 2 is 0.1. That is Cu plus 2 concentration. Cu plus 2 concentration is 0.1. Now we need to find the Ag plus concentration. E cell also given in the numerical, that is 0.422. That is the cell potential. Cell potential means E cell. So we know 0.422 is equals to 0.46 minus 0.0296. After dividing this into log 0.1 is minus 1 minus 2 log of Ag plus. So therefore, we got this value finally. So finally we can find the Ag plus concentration is anti-log of this value. So after calculating anti-log value, we will get 0.0722. Yes. So this is the numericals on Nernst equation. So let us move on to the next topic, that is reference electrode. But before going to see the reference electrode, we have seen the electrochemical series. Yes, in electrochemical series, what is the standard electrode? By using which electrode we are finding the electrode potentials of the remaining electrodes? By using standard hydrogen electrode. Yes, here standard hydrogen electrode is The electrode whose electrode potential value is known and remaining electrodes values are unknown. So by using known electrode, we can find the electrode potential of the unknown electrode. Yes. So already I explained in the previous class. Let us assume these are the two electrodes. One is the unknown electrode and other is the known electrode. So by using the known electrode electrode potential value, we can find the unknown electrode electrode potential value by connecting these two electrodes with the voltmeter. Here, what voltmeter is displaying? Voltmeter is displaying the E cell value or EMF value. Yes. So here EMF is nothing but E cathode minus E anode. So we know the EMF value and E cathode value. Then we can find the unknown electrode electrode potential value. So now let us see. Maybe you can understand after I explaining this. So reference electrode is nothing but reference electrodes are the electrodes with reference to those the electrode potential of any electrode can be measured. Yes, that means by using reference electrode, we can find the electrode potential of any electrode. That means the reference electrode electrode potential value is known. We can define in another way. Reference electrode is nothing but the electrode whose electrode potential is known, which is used to determine the electrode potential of unknown electrode or any electrode. It can act both as an anode or cathode depending upon the nature of other electrode. I said, this is the reference electrode whose electrode potential value is known, and this is the unknown electrode whose electrode potential value is unknown. Yes, this is the reference electrode. This is acting as either cathode or anode. It is depends on the other electrode potential value. So how can we say? Based on the electrochemical series. For example, if it is at the top position in electrochemical series, obviously it will be bottom position in electrochemical series. Top one is anode, bottom one is cathode. Yes. So like that, the reference electrode acting as anode or cathode. The reference electrodes can be classified into two types. One is primary reference electrode and other one is secondary reference electrode. A primary reference electrode example is only standard hydrogen electrode, which we have seen in electrochemical series. Secondary reference electrode is calomel electrode, silver chloride electrode. It is also called as the glass electrode. And another electrode is quin hydrone electrode. So we are having so many secondary electrodes, but in our syllabus, we are having saturated calomel electrode, glass electrode, quin hydrone electrode. Yes, here the primary reference electrode values are always equals to 0, but secondary reference electrode values are not equals to 0. It is having some value. Yes. So that means standard hydrogen electrode potential value is always equals to 0. So now let us see the construction of standard calomel electrode. How to construct standard calomel electrode? Calomel electrode is a metal salt ion electrode. That means it is containing metal and also metal ion. It consists of mercury, mercurous chloride, and a solution of potassium chloride. So here metal is mercury, metal salt ion is mercurous ion. So it is also called as metal salt ion electrode, and it consists of mercury, mercurous chloride, and the potassium chloride. Mercury is placed at the bottom of a glass tube. So this is the construction here. Mercury is placed at the bottom of the saturated calomel electrode or the standard calomel electrode, and a paste of mercury and mercurous chloride is placed above the mercury. A paste of mercury, mercurous chloride. The bottom is coated with the mercury, and above this mercury, mercurous chloride paste is coated. And the space above the paste is filled with a potassium chloride solution. known concentration. So here the entire tube is filling with the non-concentrated potassium chloride solution. So what is there at the bottom? At the bottom we are having the mercury paste. Above the mercury we are having mercury mercurous chloride, and the tube is filling with a non-concentrated potassium chloride solution. So I'll explain you later why we are using the non-concentrated potassium chloride only here. Yes, and a platinum wire is kept immersed in the mercury to obtain the electrical contact. So this is the platinum wire, and this platinum wire is responsible for the electricity. And calomel electrode can be represented as mercury, mercurous chloride by potassium chloride. So now let us see how to write the cell notation. Yes, I explained you in the previous class how to write the cell representation. Yes. So how to write the cell notation? Anode electrolyte, double vertical line, cathode electrolyte, cathode. Anode electrolyte, anode single slash anode electrolyte, double vertical line, cathode electrolyte slash cathode. So now what we are assuming here, the saturated calomel electrode is acting as the anode. I said you know, it is acting as either anode or cathode, that is depends on the other electrode. Now what we are assuming, saturated calomel electrode is acting as the anode. If it is acting as the anode, to the double vertical line, left side part is matters here. We need to consider the left side matter, left side one here. What is the left side one to the double vertical line? That is anode slash anode electrolyte. That means first we need to represent anode, then anode electrolyte. So what is the anode here? Anode is mercury mercurous chloride, which is coated with the platinum. Yes. So which is coated with the platinum. So we can write platinum, which is coated with mercury mercurous chloride, because for supplying electricity, what we are doing, the platinum is dipping in mercury mercurous chloride. So it is enhancing the power supply, the mercury mercurous chloride. So the platinum mercury mercurous chloride slash electrolyte. What is the electrolyte here? Potassium chloride. It is also called as the calomel. Yes, potassium chloride. So if it is acting as the cathode, reverse. First we need to write KCl slash platinum mercury mercurous chloride. Yes, we need to write reverse in the case of cathode. Yes, so again I will read out once. Calomel electrode is a metal salt ion electrode. It consists of mercury mercurous chloride and a solution of potassium chloride. Mercury is placed at the bottom of the glass tube, and a paste of mercury mercurous chloride is placed above the mercury. The space above the paste is filled with the potassium chloride solution of known concentration, and a platinum wire is kept immersed into the mercury to obtain the electrical contact. And this is the cell notation of saturated calomel electrode. So now, depend on the nature of the other electrode of the cell, the calomel electrode can act as anode or cathode. So now we are assuming, we are writing the reaction here for the reduction reaction. So we are assuming it is acting as a cathode. So we are writing the reaction for the reduction. So this is the reduction reaction. So we are having the mercurous chloride here and mercury here. This mercurous chloride is gaining the electrons to produce the mercury and chloride ions. So mercurous chloride plus 2 electrons giving rise to 2 mercury plus 2 Cl minus. 2 mercury plus 2 Cl minus. Yes. So here mercury is the paste here, not liquid. It is a paste. So it is considered as a solid only. It is not the liquid. So now let us apply the Nernst equation to this reaction. So we are considering the reduction reaction for the reduction reaction, we are writing the Nernst equation. So what is the Nernst equation? General Nernst equation is equals to E naught minus 2.303 RT by NF log A. Because we don't know the temperature, whether it is the room temperature or the normal temperature, for the temperature. So we are considering the general Nernst equation. E is equals to E naught minus 2.303 RT by NF. N is the number of electrons to F log Q. What is Q here? Product concentration divided by reactants concentration. So what is product here? Mercury power 2, because number of moles must be on the power. Cl minus power 2 by Hg2Cl2 concentration. But here we know Hg is the solid, Hg2Cl2 is also solid. But we know solid concentration is equals to 1. So that means this concentration is equals to 1. This concentration also equals to 1. So by substituting these values, we can write E naught minus 2.303 RT by 2F log Cl minus H square. So it is log A square. Log A square means 2 log A. So E naught minus 2.303 RT by 2F into 2 log Cl minus. So when we cancel 2 and 2, we will get E naught minus 2.303 RT by F log Cl. Yes. So this is the Nernst equation for saturated calomel electrode or the standard calomel electrode. So therefore, electrode potential of calomel electrode is depending upon the concentration of KCl. The electrode is reversible with chloride ions. See here, this electrode potential value always depends on the potassium chloride concentration here. If we don't have the Cl minus, it is not depends on the concentration. But see here, the electrode potential always varies by changing in the concentration of potassium chloride. If we use the saturated potassium chloride, the E value is 0.241. That is the electrode potential of saturated calomel electrode. If we use 1 molar potassium chloride, the electrode potential is 0.281. If we use 0.1 molar potassium chloride, electrode potential value is 0.334. Yes. So the electrode potential value is varying by changing in the concentration of potassium chloride. Yes. So this is saturated potassium chloride or standard calomel electrode diagram and the working condition. So now let us see what are the applications. So no need of this measurement of so let us see the applications of saturated calomel electrode. It is used as a secondary reference electrode in the measurement of single electrode. Yes, so it is used as a secondary reference electrode in the measurement of single electrode. That means we can find the unknown electrode potential value. Yes, saturated calomel electrode is acting as a secondary reference electrode to find the unknown electrode potential. It is used as a reference electrode in all potentiometer determination and to measure pH of the given solution. Yes, it is also using in the potentiometric titration in the chemistry lab. I will show you how the saturated calomel electrode in the chemistry lab. Yes, so it is used in the potentiometric titration to find the electrode potential value and also used to find the pH value. So this is standard calomel electrode or the saturated calomel electrode. So now let us see the last one, that is the quin hydrone electrode. So saturated calomel electrode is having the structure. It is available in the metallic form, but whereas quin hydrone electrode is not available in the electrode, that means it is not available in the solid form. It is available in the powder form. So you don't have any diagram for the quin hydrone electrode. You don't have any diagram for the quin hydrone electrode because it is not having any structure. It is available in black shiny powder form. The quin hydrone electrode is the equimolar powdered mixture of quinone and hydroquinone. Yes. Here the quin hydrone electrode is nothing but it is containing quinone and hydroquinone in the equal portions. By mixing these two in the equal portions, we can prepare the quin hydrone electrode. So that is equimolar mixture of quinone and the hydroquinone. That means those two are with the equal portions and the equal concentrations in the quin hydrone electrode. And it can be used to measure the hydrogen ion concentrations and the pH of a solution containing an acidic substance. It is used to find the H plus ion concentration. But where H plus ions are present? H plus ions are present in the acid only. Yes. So it is applicable only for the acidic solutions. That means we can't use this quin hydrone electrode in the basic conditions. We can use only in the acidic conditions to find H plus ion concentration and also to find the pH of the given solution. And let us see how to construct the quin hydrone electrode, because there is no construction of quin hydrone electrode because it is available in the powder form. So we need to represent quin hydrone electrode as the electrode. So to show this as the electrode, we are using another reference electrode, other electrode. Yes, that is the supporting electrode. That supporting electrode is a platinum electrode. A platinum wire electrode is immersed in a saturated aqueous solution of quin hydrone. So what we are doing? We are preparing the saturated aqueous solution of quin hydrone. What is the aqueous solution? Aqueous solution is nothing but the solution which contains water as a solvent. That means we are taking the quin hydrone powder and that we are mixing in the water and the acid, because it is used only in the presence of acid. So first it is mixing in the water and then it is mixing in the acid. And in this acid, what we are doing, we are dipping the platinum electrode. So now the platinum electrode is dipping in the quinone, quin hydrone and the acid. So now it is able to supply the electricity, because the platinum wire is there, it is responsible for electricity. Yes. So this is the construction of quin hydrone electrode. But I said you, it is the equimolar mixture of quinone and hydroquinone, quinone and hydroquinone. But here, when the platinum wire is dipping in the acid, or when quinone and hydroquinone are mixing in the acid, the quinone in quin hydrone is converts to hydroquinone and hydroquinone converts to quinone by gaining the H plus ions from the acids. So see here, this is the hydroquinone. This is the structure of hydroquinone. Hydroquinone is losing two H plus ions to convert quinone. Yes, hydroquinone is losing H plus ions to convert quinone. And also, quinone is gaining two H plus ions to convert hydroquinone. So this is always a reversible reaction with same speed. Yes. So here there is a forward reaction and backward reaction when the quin hydrone electrode is mixing in the acid. Yes. So this is only the responsible for electricity and producing the electropotential value. So this quin hydrone can be mentioned as QH2 because we can't apply the Nernst equation for the diagrams. So simply what we are doing, the quin hydrone can be mentioned as QH2, quinone can be mentioned as Q plus 2H plus 2 electrons. So now let us apply the Nernst equation. The potential difference between the platinum electrode and a reference electrode is depending on the activity of hydrogen ions in the solution. So here the potential difference is nothing but the electrode potential E value or E cell value is depending on the H plus ions concentration. Like potassium chloride concentration, it is depending on the H plus ions concentration. That means acid concentration. If the acid concentration is changing, E value also changing here. Now let us apply the Nernst equation. What is the Nernst equation? E is equals to E naught minus, not plus here, E naught minus 2.303 RT by NF log K. But what is K here? K is products concentration divided by reactants concentration. Yes, products concentration divided by reactants concentration. So 2.303 RT by what is N? N is 2F log product is Q H plus power 2 divided by QH2 concentration. But we know quinone and hydroquinone, these two are in the equal portions and equimolar. That means concentrations of quinone and hydroquinone are same. So when these two are same, we can get cancelled. We can cancel these two. So remaining is E naught minus 2.303 RT by 2A log H plus power 2. Same like previous, log A square to log A. So this 2 we can write here or here. So E naught minus 2.303 RT by 2F log 2H plus. So this 2 gets cancelled. We will get E naught minus 2.303 RT by F log H plus. So see here, the electrode potential value is depending on the concentration of H plus. If H plus concentration is changing, the electrode potential value also changes. So this is the Nernst equation. And finally, we can write one more here. E is equals to E naught minus. So what we can write here? Minus log of H plus. So have you seen anywhere? Minus log of H plus is nothing but pH. pH is equals to negative logarithm of H plus concentration. So in the place of minus log of H plus, what we can write? We can write pH. So we can write here plus 2.303 RT. What is minus log of H plus? Minus log of H plus is pH. Yes. So that means we can find the pH value if we know E naught value and E value. Yes. So by using the Nernst equation of quin hydrone electrode, we can find the H plus ions concentration and also we can find the pH of the unknown solution. So the quin hydrone electrode provides an alternative to the most commonly used glass electrode. Yes, we are having one more topic that I will explain you in the next class. I told you the glass electrode. So glass electrode is the alternative electrode of the quin hydrone electrode. However, it is not reliable above pH 8. The characteristics of glass electrode and the quin hydrone electrode are same. Both are used to find the pH value. But the quin hydrone electrode is used to find the pH value up to 8. But we are having up to 14 pH values. But it is used to find the pH value 8 correctly. But after pH 8, we can't find exactly and cannot be used with a solution that contains a strong oxidizing or reducing agent. Yes, that means if you are having the strong oxidizing agents, strong reducing agents, we can't find those electrodes, electrode potential value by using quin hydrone electrode because we can't find exactly by using the quin hydrone electrode. So that's the reason we are using the glass electrode to overcome those drawbacks. So glass electrode is used to find more than pH 8. That means we can find up to 14 pH value. And it is also useful to find the electrode potential of the strong oxidizing agent and the strong reducing agent. Thank you so much.